Okay, so today I'll be talking about range query algorithms. And let's see, can I? All right, so I can draw on my screen. That's great. Okay, so um, introduction. So what are range query algorithms? So first, what are range queries? Range queries it's like an operation that takes in a subarray of some certain array and outputs a result based on the values in that subarray. So if you have an array and you have a range query from I to j, it's basically doing some function on the values from ai plus 1, I plus 2, so on all the way to j. And in general, range queries can be used for any type of problem that will involve operations on an entire range of an array. So here's an example. If you have an array, it has n elements, and n is at most 10 to the fifth, and you have integers I and j, you want to find the sum of the range ai plus 1 plus ai plus 2 all the way to aj. So this problem is actually pretty easy. You just loop through the array and add all of the numbers up. So here's a sample implementation. As you can see, it's only 20 some lines. So here's a second example, which is a bit harder. And basically what it's asking is you want to do the same thing, but you need to do it q times for q queries. And for each query, you're given different numbers I and j. And you want to find this sum for q pairs of integers I and j. So let me give an example. So let's say our array is 1, 5, 3, 6, 9, 4. So we can have one query that's from 2 to 5. So we'll need 5 plus 3 plus 6 plus 9. And then if our second query is from 1 to 3, then we need to also output 1 plus 5 plus 3, and then so on. So what happens when we try to use our previous solution? Well, each query, if we go back, our complexity here was O of n because we have to add almost n numbers. So if we go here, we have q queries, and each query is O of n, so our total is O of n q. But when you go back, n is 10 to the fifth, and q is also 10 to the fifth. And when you multiply them together, you'll get 10 to the power of 10. And so that is too slow. So to do this, I'll introduce an algorithm called prefix sums. So what are prefix sums? Basically, you will calculate a prefix sum array, and each element p of I is the sum from k is 1 to I of ak. So what that means is if we use this array again, the first prefix sum, that's just a of 1, which is 1. The second prefix sum is 1 plus 5, which is 6 here. And then 1 plus 5 plus 3 is 9. 1 plus 5 plus 3 plus 6 is 15. And then 1 plus 5 plus 3 plus 6 plus 9 is 24. So our prefix sum array will just be this array, 1, 6, 9, 15, 24. Okay. So how can we use this to solve our problem? Well, we want to find our query here, and we can actually express this in terms of our prefix sums. So if you notice, this is prefix sum of j if we write down the definition of p of j, and this is p of I minus 1. And when you subtract these two equations, what you'll get is this, which is what we wanted to find, and it's equal to p of j minus p of I minus 1. So what we do is for each query, we don't have to add up all of these. We can just use p of j minus p of I minus 1. And if we have the prefix sum array, well, then we can find this in O of 1. So the solution is to create a prefix sum array, and then for each query, we can just use our formula that we got. And we can calculate the prefix sum array in O of n, because if we use our previous example array, 1, 5, 3, 6, 9, what you would do is you would just keep track of 1, and then you would add 5 to get the next number, and that's 6. And then to get the next number, you would just add 3, and then that's 9. And then you can see we can just add the current number in the array at our index to our previous prefix sum to get the next prefix sum. This will become clear in the sample implementation if you're a bit confused, hopefully. So our final time complexity is O of n plus q, because O of n to construct a prefix sum array, and then after that each query is O of 1. So here's our sample implementation, and you can see here, instead of like having a loop to calculate each element in the array, what we can do is just do array I plus equals array I minus 1, and this will calculate the prefix sum array in O of n. Okay, so here's another example. This is a silver problem, and what it says is Farmer John has n cows, and they're standing in a row, and each cow has a distinct integer ID number. So, and Farmer John wants to take a photo of a contiguous group of cows, but their ID numbers have to add up to a multiple of 7. And what you want to find is the largest group he can photograph. So here's the input formula. We can see n is 50,000. So we can't like brute force this. That would be too slow. And here's the sample input. So the formatting is a bit weird, but n is equal to 7. That's 7 here. And these are the IDs of the cows. And the sample output, in this case, that would be 5, because we can notice that this subarray here, 5 plus 1 plus 6 plus 2 plus 14, that's equal to 28. And 28 is a multiple of 7, so we're good there. And you cannot create a larger array, subarray, that sums to a multiple of 7. So in this case, there are 5 numbers here, so the answer is 5. And so the algorithm here is we can use our prefix sums to calculate the sum of a certain subarray in O of 1, but actually that'll still be too slow because n is 50,000 here. And if we just brute force and loop through all possible subarrays, there are n squared subarrays, and 50,000 squared is too big. But luckily, what we can do is keep track of the prefix sum, but only keep track of the mod 7. So what will happen is we'll have 3, and then the next one will be 8, but since we're only interested in mod 7, we'll do 1, and then 2, and then 1, and then 3, and so on. And if we want a subarray to have a sum that is a multiple of 7, well, that will mean that the two prefix sums are the same. For example, 3 and 3. So when we have this subarray, the sum of this, using our formula from a while back here, it'll be mod 7, it'll be the same as 3 minus 3, which is 0. So this one is 0 mod 7. And so the problem reduces to what we want to find the longest contiguous subarray such that the two prefix sums at the endpoints are the same number. Okay, and so to do this, we can just keep track of the earliest occurrence of some number and also the latest occurrence of some number. So if we have like 3, 2, 4, 1, something, something, 3, 4, 1, what we would do is we say, well, if we want 2 3s, we might as well take the earliest 3 and the latest 3, and that will be optimal if we want 2 3s. And if we want 2 4s, we would take the earliest 4 and the last 4. And so you would do this for 0, 1, 2, 3, 4, 5, 6. And then you'll take the max of all of those. And so here's a sample implementation. And notice that this is in Java, which is highly not recommended, but that was the solution on the USICO website. And yeah, it's what I was describing. You would have an array. This one keeps track of the first occurrence, and this one's for the last occurrence. So what's happening is they're just reading in all of the numbers and keeping track of the current prefix sum, which is curpref here. And then for each possible remainder, you would calculate the last minus the first occurrence, and that's the length. And so yeah, that's how you implement that. So now my next section here is about dynamic range queries. And so what are dynamic range queries? And the idea is dynamic range queries are basically range queries on an array that it's possible to change. So let me, yeah, so the array can change, and I think it'll become more clear if I give this example. So it's similar to last time, but now there are two types of queries, which is the first type is two integers I and j are given, and you want to output the sum of the range, and that's the same as last time. But the second type of query is two integers I and x are given, and I is the index, and x is like the new value. So what you want to do is change the value of the array at index I to x. So I should probably give an example of this. So let's say your array 1, 3, 2, 5, 9. I don't know. So let's say you can have a query which is find the sum of this subarray, so you would answer 10. And then you can also have a query that says, okay, change the value of this element to, let's say, 13. And then when you get another query that says sum this subarray, now you have to output 21, because now this value is 13, so you want 3 plus 13 plus 5. And of course you can update as many as you want and query as many as you want, but the total number of these two will be q, and that's 10 to the 5th. Okay, so, okay, I'm going to skip to one of my slides first, in the end first. So, I'll explain why prefix sums does not work here. So, oh shoot, O of n, not O of log n. Okay, so here if we had a prefix sum array, 1, 3, 5, 9, 2, 13. Okay, so we construct a prefix sum array here. But let's say we wanted to update this one. This one is now 4. Well, what happens to our prefix sum array? Well, actually, we'll have to update every single value in our prefix sum array, right? This one changes to 4, this one to 7, this one to 12. All of them have to get increased by 3 because the first value was increased by 3. So that means that updates are O of n, and that is not good because that will make the total time complexity O of nq. And again, that's too slow because n is 10 to the 5th and q is also 10 to the 5th. So that will not work. So now I'll introduce segment trees. And so what are segment trees? It's kind of hard to explain, but basically a segment tree is a type of binary tree, and the nodes contain the values of a certain subsegment of the array. So they're kind of like prefix sums, but they're not from the first element to the ith element. They're different subsegments. And the tree is built in a way such that if you want any range, at most O of log n nodes need to be summed. And this might be a bit confusing, but I'll give an example here. So here's a diagram of a segment tree. So at the bottom here, this is our array. So 1, 5, 2, 6, 3, 4, 3, 8. And these are nodes. So these are all nodes. And technically, these are also nodes. So what do these nodes contain? Well, this node contains, by the way, the nodes are linked like this. So this node has 2 children. This node also has 2 children. Each node has 2 children. And it looks like that. And so what does each node contain? For example, this node contains the sum of this interval, so that's 6. This node contains the sum of this interval, which is 8, and then so on. And then these two nodes, well, this node contains the sum of this big interval, which is the sum of these two, which is 14. And then same thing, this node contains the sum of this interval. And then this node at the very top contains the sum of the whole thing. And so that's how they are built. And so yeah, as I said, each node represents the sum of a certain range. And each node's children, their ranges divide the node's range into half. So if this node is like this range, then this node's left child is the left half of the range, and the right child is the right half of the range. And you can notice that this number is always the sum of these two numbers, which will be useful kind of later on. Okay, so why are segment trees useful? Well, for calculating the sum of any range, we will need to sum at most O of log n nodes. So for example, the indicated range here, if we wanted to sum this range here, instead of doing 5 plus 2 plus 6, 3, 4, 3, 8, instead of doing all that, we can just sum these 3 nodes. And if you see these 3 ranges, they add up to the big range. So we only need to sum these 3 nodes. And okay, so another example, for this range here, we would only need to sum these 3 nodes instead of all of these nodes here, because these 3 ranges add up to the big range that we want. Okay, so why does this work? Like, why is it always O of log n? So if you think about it, the segment tree, it has rows, right? So like first row, second row, third row, fourth row, there are 4 rows here. And from each row, we will need to sum at most 2 nodes. And so why is this? Well, assume for the sake of contradiction that there are 3 nodes from one row. So let's say we're summing this, let's say we're summing this node, and this node. And they have to be next to each other, because we're summing a contiguous range. So they can't be like this node, that node, whatever. So they're next to each other. Well, we'll get a contradiction here because we'll consider the parities. Well, yeah, and Okay, this is not the intuitive way to think about it. But the intuitive way is, let's say if we have 3 nodes, there will always be 2 nodes here, in this case, these 2 nodes, that we don't want to sum. Instead, we can just take this node because it's the same as the sum of these 2 nodes, right? So we don't sum these 2 nodes, we just sum this node. And same thing if we have like these 3 nodes, now we can combine these 2 nodes into this node. And if you want to prove this rigorously, you can notice that if you look at the indices like 1, 2, 3, 4, 5, 6, 7, 8, it's either odd, even, odd, or even, odd, even. But whenever you have an odd node followed by an even node, you can do the merging thing that we just talked about and merge it into the parent node. And notice that both of these cases have an odd node followed by an even node. And so we'll get a contradiction, and so that means that we won't have to sum more than 2 nodes. And there is one corner case, which is when you're summing. So we originally we assumed that they must be next to each other, and there is one corner case, which is when one of these nodes from the row is on one side and one of them is on the other side. But this argument still works because you can see if we add another node to each of these sides, we'll get the merging thing again. So the argument still works, and we'll need at most 2 nodes from each layer. Okay, so the time complexity for a query is O of log n because there are log n layers. But actually this is slower than our prefix sum solution, because remember, if we go back to our prefix sum solution, we can just use this formula. It's O of 1. So why is this useful? And I already talked about this. And it is because the thing where we're updating a node. So what happens when we update a node in prefix sums? Well, we just talked about that updates are O of n. But if you look at our segment tree here, let's go to a better diagram. So let's use this diagram. Let's say we wanted to change this node. This node is not a 3. It's now 10. Well, how many nodes will need to be changed? We need to change this node, of course, and also this node, and this node, and this node, but none of the other nodes have to be changed. So we need 1 node from each layer, and there are log n layers, so we'll only need to change log n nodes. And so that's why updates will be also O of log n, while updates in our prefix sums algorithm is O of n. Therefore, our final complexity will be O of q log n. Okay, technically also plus n, because it takes O of n time to build the tree. All right, and that will run in time because log n is not too big. So segment trees are actually they're not just good for this one update a point and then compute the sum. Segment trees, well, first of all, they can also support range updates using something known as lazy propagation. And basically what that means is, so here, instead of updating a single point, well, I'll update an entire range. So let's say, okay, everything in here, now they're all 5. So it can also do that in O of log n using lazy propagation. And you can use them with other data structures. So for example, not just arrays, but you can use segment trees on regular trees. So if you have like a regular tree like this, one common trick is to do a DFS on the tree and basically reduce the tree into an array. So this is number 1, 2, 3, 4, 5, 6, 7. And that's called a DFS ordering. And one useful application of this, it's in one of my problems here that I listed, is that whenever you want to update a subarray, well, let's say you wanted to update this node subtree, it's just a subarray 2, 3, and 4. And this probably wasn't the best example. If we had like a big tree, there's some stuff here, like very big. We can update all of these nodes by saying if this is like 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We can update all of these nodes by just updating the subarray from 3 to 12. And there's also a technique called HLD, which stands for heavy light decomposition. And what that does is you can have a tree. This is also a tree algorithm. And you can decompose it into paths. So what will it be? So you would make heavy edges, which is basically the edge that goes to the heaviest subtree. In this case, these will be heavy edges. And each path, it turns out each path from one node to another can be written as the sum of O of log n heavy paths. So like heavy paths will be just connected heavy edges. So there, there, and there. And there are also many different types of other range queries that can be solved with segment trees. And these are just some examples of past USICO problems. And you can see that these are mostly platinum problems, right? So they're mostly platinum problems, but actually segment trees have been showing up in gold contests recently. So I would also recommend studying them if you're planning on taking gold. And so, oh yeah, so this is just one example. In this problem, you have there's a restaurant and you're seeding cows at contiguous ranges and stuff. it's a pretty cool problem. Yeah, I would recommend you check out some of these problems if you want. And so, yeah, that's it. So thank you for listening.